Hey everybody, I'm going to be talking you through one of the sample questions or one of the exercises that I had you go through while that day I was gone. So you might want to go into Notability and open up the N2L problem solving practice that I assigned that day, just to go through it again and make edits as you go. You can also find this exact same question worked out on page 65, but I thought maybe it'd be easier if I talked you through it. Because as I went through the forms that were turned in, I could tell that some of you were missing some steps. The instructions included going back to page 65 in the text and checking your work against that and editing it. I don't know if that instruction got missed with the sub or if some of you just ignored it and moved on, but it's important that you understand this problem solving process. So I'll try to get through this as quickly as I can, but also making sure that you understand how the process works. So first thing I want to do is I want to sketch the process. So take a look. Earth exerts approximately a 100 Newton force on a 10 kilogram suitcase. Suppose you exert an upward 120 Newton force on the suitcase. If the suitcase starts at rest, how fast is it traveling after lifting it uh, for basically half a second? So first thing I'm going to do is I'm going to sketch the process. So I'm not going to get too crazy with this. This is my art skills here. I've got my suitcase and my arm, and there's my hand lifting the suitcase, and I'm going to show that it's moving with, the little cartoon motion lines. And so there, done. Choose the system. Draw a dotted line around it in your sketch. So what's my system in this case? Since these forces are being exerted on the suitcase, I'm going to make the suitcase my system. So I'm going to draw a dotted line around that to remind me. So I've done that. Choose a coordinate system and label it in your sketch. I'm actually going to come back to this in a little bit. Label the sketch with everything you know about the situation, including accepted physics symbols and units. This is a major step that a lot of you are missing when I'm reviewing the work that you've done. So I'm going to go through and I'm going to find out everything I know about this. It says that the Earth exerts that much force on the suitcase. So first thing I'm going to label it with is, actually I'm going to put this down here closer to the Earth. Force of the Earth on the suitcase is 100 newtons on a 10 kilogram suitcase. So something else I know about the suitcase is that it has the mass of the suitcase is 10 kilograms. Says suppose you exert an upward 120 Newton force on the suitcase. So the force of I'll say the hand on the suitcase is 120 newtons. If the suitcase starts at rest, so that tells me that as it's being lifted from the ground, its initial velocity is 0. How fast is it traveling after lifting? So for this much time. So the time interval that is being lifted is this 0.50 seconds, and so that tells me that that's a list of everything I know, and it says identify the unknown that you need to find and label it with question mark in the sketch. And something I should have included here is make sure you use accepted symbols. So something I don't know the final velocity of that suitcase. And as well, I'm going to come back. So I don't know the final velocity of that suitcase. So that's what I'm looking for. So I've finished everything in the sketch and translate except for that coordinate system. I'm going to come back to that. All right, so I move on to simplify and diagram. Make the appropriate simplifying assumptions about the process. All right, for example, and there's a couple examples given. Can you neglect the size of the system? Well, yeah, we don't care how big that suitcase is for this purpose. In other words, we can treat it as a point object. All right, and then can you assume that the forces or acceleration are constant? And yes, in this case we have to, because the rules that we have so far assume that that we have a constant acceleration and a constant force. So those are my simplifying assumptions. Then it says draw a motion diagram of the process. So I've got my suitcase that started at rest. It's lifting upwards off the ground, and I can already actually, you know what? I'm going to start with a force diagram because I know a little bit more about the forces involved. I know that the force that's being exerted by the hand on the suitcase is larger than the force exerted by the earth on the suitcase. And I want you to notice I wasn't really concerned with drawing those two force vectors to scale as much as I was concerned with showing that the force that's in the upward direction is larger than the force that's in the downward direction. That's important because it tells me, it indicates to me that the acceleration of the system is going to be upwards. So that tells me that that informs my motion diagram, that now I know that it's going to start at rest and it's going to get faster as that force is exerted on it. So at this point, here's why I waited to do my coordinate system. Here's a little pro tip for you. The way I choose my coordinate system is I basically determine, if possible, in what direction the object is going to accelerate. And then once I determine that, that's how I decide which part of my coordinate system is going to be the positive direction, the negative direction. Since the acceleration in this case is directed upwards, I'm going to refer to up as the positive direction and down as the negative direction. So now I've got my coordinate system labeled. I've got my motion diagram. I've got my force diagram. And then I want to make sure that they're consistent with each other, which is something I noticed that some of you missed in that work the other day. Well, let's see. How do I know if they're consistent with each other? The upward force is larger than the downward force, which tells me that the net force is directed upwards. Well, from our rules, we know that if the net force is directed upwards, the acceleration is going to be in that same direction. So my motion diagram shows an upward acceleration, and my force diagram shows an upward net force, so they match. So I've got that taken care of. So now I move on to a mathematical representation. Convert these qualitative representations into quantitative mathematical descriptions using kinematics equations and Newton's second law for motion along the axis. So what does that mean? We developed in class a mathematical model for Newton's second law of motion, and that is that the acceleration of the object is determined by the force acting on the net force acting on that object, on the mass of that object. In this case, and then I'm going to point out this next point. It says determine the signs for the force components in the equations. This is based on my coordinate system. I've called up positive and down negative. So this is where I go to my net force and I ask myself, what force or forces are combining to create this, to be a part of this net force? Well, it'd be the upward force of the hand on the suitcase, which I've designated up as a positive direction. And since this means sum, I'm going to add the other force, or in this case, there's one other force, the force of the earth acting on the suitcase, which by my coordinate system, I've determined is the negative direction. And those forces combine to provide combine for the net force that's acting on that mass. So that's what is meant by the force components in the equation. So we took care of that. I've got my mathematical model for the force, but there's something I just realized here. So that net force that's acting on that suitcase is going to cause that mass to accelerate. There's something I don't know yet. I don't know that acceleration. So I'm going to go back up here because this is something else I want you to notice about or know about these steps. They're not static. They're not set in stone. If I need to go back up and change something, I'm going to change it. I just realized that I don't know the acceleration of that system. So I'm going to need to know it. And why is it important for me to list my my givens and my unknowns? Because I need to identify the right mathematical model to use for this situation. Well, in this case, if I want to find, let's see, if I want to find the final velocity, I'm going to, let's see, Newton's second law is going to tell me the acceleration. So this will become a given value to help me determine this value. So I need something that includes, I need a kinematic expression from my notes or from my equation sheet that includes all of these four variables. So I'm taking a look at on my notes and on my equation sheet right now, and I see something that looks like this, that the final velocity of an object at any given time is equal to the initial velocity of that object plus the acceleration of that object times the time interval, in other words, how long that object has been moving. That'll get me the final velocity. So I have converted both of these, I've converted both of my diagrams into my visual models into mathematical models, and I've added the force components with either positive or negative signs to find the sum of the forces. All right, that's what I did in this step right here. So now I move on to solve and evaluate. Substitute the known values for the mathematical expressions and solve for the unknowns. And something else I should have added here is include units. So that's what I'm going to do. I need to find the acceleration of that object by Newton's second law. And actually, let's see, I don't need all of that. Here's what I'm going to do. I'm going to say the acceleration is equal to, since we already determined what that net force is equal to, it's the force of the hand on the suitcase. Now remember, that was in the positive direction, plus the force that the Earth is using in the suitcase. Well, that plus and negative, that's the same thing as saying minus the force that Earth exerts on the suitcase. And both those forces are acting on that mass. So then I plug in those values. The force of the hand on the suitcase is 120 newtons. The force of the Earth on the suitcase is 100 newtons. The mass of the suitcase is 10 kilograms. So let's see, 120 minus 100, that is 20. 20 divided by 10 is 2. And what would the units be? It'd be a Newton per kilogram. But if I break that down, that ends up being the same as a meter per second per second. So there's my acceleration. Now I can go back and find that final velocity because now I've got all the information I need for that. The final velocity is equal to the initial velocity plus the acceleration times that time interval. We know that looking up at my first step there, I know the initial velocity is 0. The acceleration now from my work, I know is 2 meters per second per second. And I know that the time interval, it was being pulled for 0.50 seconds. So let's see, what's 2 times 0.5? 2 times 0.5 is 2 times 1/2. That's 1. Meters per second over seconds times seconds over that imaginary 1. Those seconds on the bottom would cancel out with the seconds in that time measurement. So that's 1 meter per second. All right, why do I bother with all of that? Well, once I've solved for everything, so I've done the solve, and then I need to evaluate my work doing things like checking the units. Well, I'm looking for the final velocity. Do meters per second measure velocity? Of course they do. So that's one way of evaluating that helps me feel pretty confident about my answer. I can also look at things like limiting cases, meaning that, I mean, in this case, I've got a built-in limiting case that the initial velocity was 0, but if that suitcase had already been moving, it makes sense that any change in that velocity would make this velocity even bigger. Another limiting case I could look at is what would happen if the mass of that suitcase was bigger or if I had exerted more force on it. Well, if I had exerted more force, that's on top of the fraction, the acceleration would get greater. Well, that makes sense. If the mass had gotten bigger, that would actually make the acceleration smaller. So that's what's meant by checking limiting cases. And then finally, make sure to check that all representations, mathematical, pictorial, graphical, all are consistent with each other. Well, luckily, I've already checked to make sure that my motion diagram and my force diagram are consistent with each other. And then when I went to that next step, the mathematical step, I double checked to make sure that all those match my coordinate system. So I'm confident there. So now I know that the final velocity of that suitcase is 1 meter per second. Uh, I hope that you went through and made those edits, because this is a problem solving process that we are going to use pretty much for any problem solving we do the rest of this year. Remember, if you need help, I'm available during GPS. I'm usually available after school. Please take advantage of that. All right. Let me know if you have any questions.